All right, today we're tackling a really cool and fundamental problem from the world of computational geometry, finding something called the convex hull. We're going to look at two of the most classic ways to solve it, gram scan and Jarvis March.
So, to get the idea, just imagine you've got a bunch of pins sticking out of a corkboard, scattered all over the place. Now, what if you took a huge rubber band, stretched it around the outside of all the pins, and just let it go? Think about the shape it would snap into. That tight boundary it creates? That's exactly what we're talking about today.
Now that whole rubber band thing is not just a cool thought experiment, it's actually a super important concept that shows up everywhere, from computer graphics and robotics to analyzing large sets of data.
And it's got a formal name, the convex hull. So what is it, technically? It's the smallest possible convex polygon that encloses every single point in your set, where the corners of that polygon are some of the original points. You can see why that rubber band analogy is just so perfect. It's not a trick, it's literally the most intuitive way to picture what we're trying to build.
Okay, so that's the what, but how do we get a computer to figure this out? I mean, it can't exactly use a physical rubber band. Well, it turns out the secret, the key to both algorithms we're going to look at, is answering one really simple geometric question. And that question is all about direction. The whole process hinges on what we call an orientation test. Imagine you're walking along the edge of this shape you're building from one point to the next. To get to the next potential point, do you have to make a left turn or a right turn? That simple decision, left or right, is going to guide every single move our algorithms make.
So how do we know if it's a left turn? With a neat little math trick using the 2D cross product. Now, don't worry, it sounds more complicated than it is. You take 3 points in order, let's call them O, A, and B. You calculate the cross product between the vector from O to A and the vector from O to B. And here's the really clever part. We don't care about the actual number we get back. All we care about is the sign. If it's positive, that's a left turn. If it's negative, it's a right turn. And if it's 0, well, all 3 points are in a perfectly straight line.
All right, now that we have our secret weapon, that orientation test, let's put it to work. First up, we've got an algorithm called gram scan. And its whole approach is super methodical, based on a classic computer science strategy.
I like to call this the sort and conquer method. The whole philosophy here is, hey, let's do all the hard work up front. If we can just get all of our points sorted in the right order from the get-go, actually building the hull becomes almost ridiculously easy.
So here's the game plan, in 3 steps. First, we need an anchor, a guaranteed starting point on the hull. We find the point with the lowest y-coordinate, that's our pivot. Step 2, we sort every other point based on the angle they make with our pivot, kind of like a radar sweep. And now for the magic, step 3, we start walking through our sorted points one by one. We use a stack to keep track of our hull's path. As we add a new point, we look back and ask, does this create a left turn? If yes, great, add it to the hull. But if it makes a right turn, that means our last move was a mistake, an inward dimple. It's like, whoops, wrong way. So we backtrack, pop that last point off our path, and check again, making sure we're always turning left.
So how fast is this? Well, the real work, the bottleneck, is that big sort we do at the beginning. And as you probably know, sorting n things is going to cost you O of n log n time. The final scan is just one pass, so the whole thing is dominated by the sort. And because we need to store the sorted points and the stack, the space complexity is O of n.
Okay, so that was gram scan. Very orderly, very planned. Now let's look at a completely different way of thinking about this. It's called Jarvis's March, but you're going to know it by its much cooler nickname, the gift wrapping algorithm.
And that name is perfect because it's exactly what it feels like you're doing. Seriously, picture the points as nails sticking out of a board. You tie a piece of string to the leftmost nail, pull it tight, and then just wrap it around the outside. You find the next nail the string hits, pull it tight from there, find the next one, and so on.
The process is just as intuitive as it sounds. Step 1, you start at the leftmost point, period. It's a guaranteed point on the hull, no question. Step 2, from your current point, you scan every single other point to find the one that makes the most counterclockwise turn. That becomes the next point on your hull. Step 3, you just repeat that process. From your new point, you again find the next most counterclockwise point, and you just keep wrapping until, bam, you've arrived back at the point where you started.
Now, the performance here is what makes it so interesting. To find each point on the hull, let's say there are O of them, we have to scan all n points to find the next one.
So the total time ends up being O of n times h. This is what we call output sensitive, because its speed literally depends on the size of the final answer. If h is super small, this algorithm is incredibly fast. But if h is big, it can really slow down. But check out the space complexity. O of 1. It uses almost no extra memory, which is a huge win.
So there we have it. Two awesome algorithms, GramScan, the planner, versus Jarvis's March, the wrapper. So, who wins? Which one should you use? Well, if you've been in computer science for more than 5 minutes, you already know the answer is always, it depends.
Think of GramScan as your reliable marathon runner. It gives you a predictable O of n log n time every single time. It's a fantastic, general-purpose, safe bet. Jarvis March is more like a sprinter. If the finish line is close, meaning h, the number of points on the hull, is really small compared to n, it can be blazingly fast, even faster than GramScan. But be careful. If you make it run a marathon where almost all the points are on the hull, its performance degrades to a sluggish O of n squared.
Now this next part is absolutely crucial, especially if you're prepping for a coding interview. Anyone can memorize the basic steps. What really shows you know your stuff is handling the edge cases. An interviewer is going to ask you, what if you have 3 points in a perfect line? Do you include the middle one on the hull or not? What's your plan for duplicate points? What happens if all the points are on one line? Your algorithm shouldn't crash. It should do the right thing. You need to have good answers for these.
So if you only remember one thing from all this, make it this. GramScan is your O(n) log n workhorse. Jarvis March is your O(n) times h specialist, perfect for when the hull is sparse. And the engine that powers them both? That simple, elegant orientation test, just checking if you're turning left or right.
But, you know, these algorithms are classics for a reason. They're from the 1970s, and that should get your brain turning. Is this the best we can do? What if you could combine the best of both worlds? An algorithm that's fast, like Jarvis, when the hull is small, but has the O of n log n safety net of GramScan, so it never gets too slow. Well, the answer is a big yes, and that opens up a whole new rabbit hole of even more clever, modern algorithms for you to explore.